All right, for question 4, it says, consider the vector field F, which is 2xi minus 3yj plus 4zk. Compute the outward flux of F across the boundary of each surface below. And in part A, S is the upper hemisphere of radius 4 centered at the origin plus the base disk of radius 4 in the xy plane centered at the origin. Okay, so we have a closed surface, right? It's the hemisphere together with the base disk. And so the divergence theorem says that to compute the flux across the surface S, we can compute that in terms of this triple integral of the divergence of our vector field over the solid region enclosed by this surface. Okay, I'll call that solid D. And here the divergence is simple. It's just 2 minus 3 plus 4. So that comes out to be 3. And here, since I'm just integrating over this solid hemisphere, this is just going to be 3 times the volume of that hemisphere. And so that's going to be 3 times 2/3 pi r cubed, and the radius there is 4. So we get 128 pi, right? Not too bad. Okay, so what about for part B? Well, pretty similar, except now S is the part of the paraboloid. Z is equal to 4 minus x squared minus y squared, and above the xy plane, together with the base disk of radius 2 in the xy plane centered at the origin. Well, it's essentially the same thing, except now I'm going to get 3 times the volume of this solid enclosed by the paraboloid and the base disk. And since this is a shape that I don't have a nice simple formula for in terms of the volume, I'll have to compute it using an integral. And here I'm using cylindrical coordinates. So z is going to vary from 0 up to the height on the paraboloid. In cylindrical coordinates, that's just going to be 4 minus r squared. And then if I project the solid onto the xy plane, we can see that x and y are varying over this base disk of radius 2 centered at the origin. And in polar coordinates, all right, that's described as r varying from 0 to 2 and theta varying from 0 to 2 pi. So those are our bounds for r and theta. Don't forget that factor of r there for the polar area element. And you go ahead and compute and you wind up getting 24 pi. All right, so not too bad. Both of these examples also again illustrate the some of the computational power of using the divergence theorem. I mean, again, the surface integral here is not impossible, but it would be pretty tedious. You'd have to compute the surface integral over this paraboloid, and we'd have to use a parameterization for that. And then you'd also have to compute the surface integral over this base disk. Okay, so while doable, certainly quite a bit more tedious than what we're doing here. All right, well, great. That's going to do it.